This is the third lecture of the series of lectures on solid angle. First, let us briefly mention the salient features of the previous lecture 2. We gave the definition of solid angle. We also found expression of solid angle. And this was what we underscored. Consider a surface element at P. This is the normal unit vector. Call it r cap. Obviously perpendicular to the surface element, which we call vector dA, equal to dA into r cap, and O is a point on this line r hat that is perpendicular to dA. Join the points of the contour of dA to O. This generates solid angle d omega given by dA by r square, where distance OP is r. Let us next consider a surface element, say at point P, and this is the normal to it. We call the unit normal as n hat. Call the surface element vector ds equal to ds n hat. Let O be a point, connect O to P, and OP is r. Clearly, O is not situated on the unit normal to the surface element ds. Join the points of contour of ds to point O, and we get a solid angle d omega. Now let us show the radial unit vector obtained by joining OP and extending it, and this is it. And this is r cap. This is r hat, the radial unit vector, obviously not normal to the surface element, that is not along n hat but inclined to it. We now construct or imagine a surface element normal to r hat, the radial unit vector, drawn at P. Call this imagined surface element vector dA equal to dA into r hat, as r hat is normal to it. The angle between n hat and r hat is theta, which is also the angle between the two surface elements ds and dA. Then the expression of d omega is dA by r square, which is equal to vector ds dot r hat by r square. Written alternately, it is ds cos theta by r square. We can also write it as ds into n hat dot r hat by r square. Obviously, dA is the projection of ds along radial unit vector. Let us next consider a surface S, an open surface, the contour of which is C. Consider a surface element of S, call it ds. O is a point, and let us join the contour points of ds to generate solid angle d omega. Join O to the point where ds is situated, extend it, call it r hat, which is the radial unit vector. Normal to ds is n hat, and we imagine the surface element perpendicular to r hat. Call it vector dA equal to dA into r hat. This surface element is vector ds equal to ds into n hat. Then d omega is dA by r square equal to vector ds dot r hat by r square, or ds n hat dot r hat by r square. Let us reiterate that dA is the projection of ds along r hat. We also popularly write it as ds cos theta by r square, and this distance from O to ds is r. The solid angle made by the entire surface S at O is obtained by joining the points of contour C of S to point O. The solid angle subtended is omega, and this is d omega. The value of omega is integration over S d omega equal to integration over S ds cos theta by r square. For closed surface S, it would be closed integration over S ds cos theta by r square. We showed that dimension of omega is m to the power 0, l to the power 0, t to the power 0, that is, solid angle is dimensionless. Unit of solid angle is denoted by SR, called steradian. Let us now move over to problem solving. First question. Find solid angle at an internal point subtended by a closed surface. Answer. For open surface, omega equal to integration over s ds cos theta by r square. For closed surface, omega is closed integration over ds cos theta by r square. Consider a closed surface S. This is it. Call it S. O is an internal point. Construct a sphere S0 with center O and radius R. This is the sphere S0. R is the radius. All lines joining O to S pass through S0 and produce the same solid angle. Look at this line. Here we draw another one very close. They intercept this area, an elemental area ds on S. Normal to it is n hat. Also, this elemental area dA is intercepted on sphere S0. The normal to it is r hat, the radial unit vector. We can extend it, and this is r hat intersecting ds obliquely. So, omega is integration over s ds cos theta by r square, or equivalently it is integration over closed surface S0 ds cos theta by r square. Now on S0, r is the radius of sphere, theta is 0, n hat equal to r hat. This is dA, a portion of sphere S0 on which n cap equal to r cap, and so theta equal to 0. So solid angle omega equal to integration over S0 dA by r square. R is the radius of sphere. R is constant, so take 1 by r square out. So we have 1 by r square integration over dA, that is 4 pi r square by r square, which on cancellation is 4 pi. Solid angle at an internal point subtended by a closed surface is 4 pi steradian. We address another question. Find solid angle at an internal point of a cube. At center of cube by any one face of cube. Answer. Let us draw a cube. This is the center O. O is an internal point. Let us draw a sphere with center O and radius R. Name the sphere S0. Construct a cone that intercepts area ds on cube surface and dA on the sphere. This is normal to ds. Call it n hat. And this is the radial unit vector r hat. Solid angle omega equal to closed integration over cube ds cos theta by r square equal to closed integration over sphere ds cos theta by r square. This is equal to closed integration over sphere dA by r square. Sphere radius r is constant, so we take it outside and we get 1 by r square integration dA over sphere equal to 4 pi r square by r square. So on cancellation, we have 4 pi steradian. This is the answer. Let us address the next part. Solid angle at center of cube, which is an internal point. This is the cube. P is center, an internal point. So solid angle omega is 4 pi steradian. Next we find solid angle at center by any face of cube. At center, omega is 4 pi, and this solid angle is created by 6 faces of cube. So solid angle created by any one face is 1/6 of 4 pi equal to 2/3 pi steradian. This is the answer. Next question. Find solid angle at center subtended by sphere, hemisphere, octant of a sphere. Answer. Consider a sphere. center is P. Clearly at center, solid angle omega is 4 pi steradian. Next, we redraw a sphere. P is center, and this is the equatorial or the xy plane. This is one hemisphere, and sphere has two hemispheres, the upper one and this one, the lower one. So solid angle at P due to hemisphere will be half of 4 pi equal to 2 pi steradian. Next part of the problem. Consider a sphere. These are the coordinate axes with center of sphere as origin. This is x-axis, this is y-axis, this is z-axis. This is the equatorial plane or the xy plane. This xy plane divides sphere into two halves. Similarly, yz plane divides sphere into two halves. So each of these two halves is further split into two portions. We thus have 2 into 2 equal to 4 halves. Let us show the 4 portions. This is 1, 2, 3 and 4. The xz plane further splits each of the 4 halves into 2, and we have 4 into 2 equal to 8 halves or portions, each called an octant because each corresponds to 1/8 portion of the sphere. As omega sphere equal to 4 pi, so omega octant, this is made by 8 portions, hence this is 1/8 of 4 pi equal to pi by 2 steradian. This is the answer. This is the solid angle subtended by octant at center of a sphere. Next question. Consider this sphere. C is center. This is an extended radius and radius is r. Consider a point B inside and another point A outside the sphere. B is at a distance r by 2 and A is at a distance 2r from C, the center. The question is, find the ratio of solid angle subtended at points A, B, C by sphere. Answer. We have shown that omega at an internal point of sphere is 4 pi. This means omega C is 4 pi because C is an internal point. Omega B is also 4 pi since B is also an internal point. C, B are both internal points. Solid angle at an external point, say point A. Let us find it now. Consider a closed surface S. Construct a sphere, call it S. A is an external point. Construct cone with vertex A. Cone intercepts area ds1 at P1. This surface element is here at P1 and call it ds1. ds2 at P2. We show it. This surface element is at P2. Call it ds2. Unit normals are outward unit normals, as is the convention. n1 cap at ds1, n2 cap at ds2. Radial unit vector is r hat. Let us show it at ds1 and also at ds2. AP1 is r1, AP2 is r2. Solid angle subtended by ds1 at A is ds1 n cap dot r cap divided by r1 square. This is equal to ds1 cos theta 1 by r1 square. The angle between n1 cap and r cap is theta 1, which is obtuse, that is greater than 90 degrees, and hence cos theta 1 is negative. Let us write it as minus of mod of cos theta 1. With this we get minus mod ds1 cos theta 1 divided by r1 square. Let us write it as minus mod d omega. So ds1 of the entering cone subtends a negative solid angle. This is the solid angle, the magnitude of which is mod d omega. Solid angle subtended by ds2 at point A is ds2 n cap dot r cap divided by r2 square. This is equal to ds2 cos theta 2 divided by r2 square. Angle between n2 cap and r cap is theta 2, which is acute, less than 90 degrees. So cos theta 2 is positive and can be written as mod cos theta 2. So we can write it as mod of ds2 cos theta 2 by r2 square. Express it as mod d omega. Solid angle subtended at A by cone is, there is contribution from ds1 plus contribution from ds2. This is equal to minus mod d omega plus mod d omega, that is 0. Actually, when the cone enters the closed surface at P1, it makes a negative contribution, minus mod d omega. But as it leaves or makes an exit from the closed surface at P2, it makes a positive contribution, mod d omega. Since the contributions are equal and opposite, they cancel out. So the cone does not contribute, since number of entries and number of exits are equal. To span the entire closed surface S, we integrate over infinite such cones. Let us show. This is the closed surface S. A is the external point. This is one cone making cuts or intercepts. This is another cone making intercepts. This is yet another cone, and so on. Integration over the closed surface means integration over the cones. Contribution to solid angle from each cone is 0. Thus, when summed or integrated, we get the solid angle at external point to be 0. Ratio of solid angles is omega A is to omega B is to omega C equal to 0 is to 4 pi is to 4 pi. That is 0 is to 1 is to 1. Next question. Find solid angle subtended by periphery of an area 1 centimeter square at a point situated 5 centimeters from the area. Answer. This is the area of magnitude 1 centimeter square. Call it A. At a distance of 5 centimeter, there is a point. Let us join the peripheral points to the point. A solid angle is created, say omega, given by definition area A by distance square, that is r square. So it is 1 centimeter square divided by 5 centimeter square, which is 1 by 25 steradian, or 4 into 10 raised to the power minus 2 steradian. This is the answer. Next question. Find solid angle subtended by moon on earth. Given surface area of moon to be 4 into 10 to the power 7 kilometer square. Orbital radius of moon is 4 into 10 to the power 5 kilometer. Answer. This sphere is for earth, represented by the center, point E, say, and this sphere represents moon. From point E, a faraway point, we draw tangents to the moon. In other words, connect the peripheral points of the moon visible from earth. And this is how we connect. We say that the moon subtends a solid angle omega at the center of earth. Actually, this portion of the moon subtends solid angle omega. The same solid angle is subtended by the circular disk portion of cross-section A that is perpendicular to the radial distance from Earth to Moon. We can take the area A to be approximately pi into r moon square, where r moon is the radius of the moon. Actually, moon is far away and this approximation is valid. No great error comes in the way. The distance from E to the moon is, say, r. Now omega equal to a by r square equal to pi r moon square by r square. Now surface area of moon is 4 pi r moon square, that has been given to be 4 into 10 to the power 7 kilometer square. So pi into r moon square equal to 10 to the power 7 kilometer square. Now r is the orbital radius of the moon, which is the same as Earth to moon distance. Moon revolves round the Earth in an orbit with this radius. It is given to be 4 into 10 to the power 5 kilometer. So omega equal to 10 to the power 7 kilometer square divided by 4 into 10 to the power 5 kilometer whole square. This gives 6 into 10 to the power minus 5 steradian. This is the answer. Next question. Find change in solid angle as planet moves from perihelion, which is 4 into 10 to the power 9 kilometer, to aphelion, which is 7 into 10 to the power 9 kilometer. Planet radius is 1200 kilometer. Answer. This is the orbit of the planet, elliptical in shape. Here is the Sun S. This point is the perihelion, the distance of closest approach. Distance is Rp from the Sun, given by 4 into 10 to the power 9 kilometer. This is the planet when it arrives here and intercepts this cone. This is the cross section of the planet, the disk area, which is perpendicular to the radial vector along Rp, and this disk area is pi r square, where r is the planet radius, equal to 1200 kilometer. This is the solid angle omega p subtended by the planet's disk area at S. This point is the aphelion, the distance of farthest approach. Distance is Ra from the Sun, given by 7 into 10 to the power 9 kilometer. This is the planet when it arrives here and intercepts this cone. This is the cross section of the planet, the disk area, which is perpendicular to the radial vector along Ra, and this disk area is pi r square, where r is the planet radius. This is the solid angle omega A subtended by the planet's disk area at S. At perihelion, omega p is disk area pi r square by rp square, equal to pi into 1200 kilometer square divided by 4 into 10 to the power 9 kilometer square. This on evaluation is 2.8 into 10 to the power minus 13 steradian, the solid angle at perihelion. At aphelion, omega A is disk area pi r square by r a square, equal to pi into 1200 kilometer square divided by 7 into 10 to the power 9 kilometer square. This on evaluation is 9.2 into 10 to the power minus 14 steradian, the solid angle at aphelion. Change in solid angle is delta omega, which is omega p minus omega A, equal to 2.82 into 10 to the power minus 13 steradian minus 9.2 into 10 to the power minus 14 steradian. Take 10 to the power minus 13 common to get this to be equal to 2.82 minus 0.92 into 10 to the power minus 13. This is 1.9 into 10 to the power minus 13 steradian. We shall do some more problem solving in the next lecture 4.